Networking is so damn cool, right? Well, what about container networking? So, container networking's been around for quite a while, and we see it everywhere we look when it comes to Kubernetes, pod networking, and even Docker networking. But what if we wanted to peel away the layers of the onion and understand a little bit more about that container networking and how these processes that are isolated are able to get out onto the network and communicate with other isolated processes as well? My name is Marino Wijay. I am here to talk to you about networking namespaces and how this all works. So let's get right into it, and we're going to dig into how this all works. So I have a diagram here that really explains just the different pieces and components of a little network. Every little endpoint needs an IP address. So for example, we can look at these two different processes here. One is called web app and the other one is called sleep. And that web app process, it has an IP address. That sleep process also has an IP address, but we want to isolate them into their own networking namespace. So we can do so. We'll wrap them in their namespaces and we'll ensure that they have a TCP IP stack so that they have a default gateway that allows them to communicate outbound. Now, in this little diagram here, our process has this virtual interface that has a wire, a virtual wire actually, that terminates at a bridge. A bridge is just another switch. And now, what effectively this bridge is doing is it's just switching traffic between the two different network namespaces. So I have one network namespace here, that is the web app, and then I have the sleep network namespace right below here. And because they're on the same bridge, they should be able to communicate very easily and flexibly. Now, when these two processes need to go outbound, what they need to do is use this default gateway, which is assigned to this bridge right here. And this default gateway address is actually going to take advantage of NAT or NAT masquerading or post routing that effectively will just hide all of these IP addresses and expose them through the actual host's physical interface to get outbound on the rest of the network. Now, how do we construct these network namespaces and how do we offboard them? Let's actually dig into that and we can see how this all looks in action. So I have a terminal here, and in fact, you should be very, very familiar with this. This is called the Google Cloud Shell Terminal, and I just decided to go with a much more simplistic setup here because I didn't want you to have to spin up a virtual machine. I didn't want you to have to spin up, your own little environment. This should be very easy. In fact, if you can get access to a Linux environment through some playground, you only need a little bit of time to get this up and running. I will share a link to a GitHub repo that you all can go check out just so that you can test this out on your own if you're interested. So let's go ahead and kick things off. Let's go ahead and make sure that we have NetTools installed. So I'm running as root on this little operating system. I don't know what OS it is. It might be some Linux variant of Google. And now I've got Linux networking tools installed. So if I did an IP route, I could see that I've got a routing table. If I did a ping to Google's public DNS server, I should be able to get outbound. Looks good to me. If I did a trace route to that same DNS server, I don't know if it'll actually, I don't have the command. Maybe I didn't install it. That's okay. I don't need it for this particular portion here, but let's go ahead and install some network namespaces. So I'll go ahead and use this command ipnetns add, we'll call the first namespace purple, and then I'll just do a double ampersand, and then we'll do an ipnetns add orange. So the moment I've done that, if I do an ipnetns, I'll see that I have two network namespaces that are active. So I should be able to go ahead and do whatever I need to them. Meaning I could start assigning IP addresses and effectively making them a part of the same network. Now, what I need to do next is I need to make sure that I can see what links are available. So the way to do that is we could go ipnetns exec purple right? We'll do one of the namespaces, and then if I do an IP link, space IP link, we'll see that we only have a loopback interface, a locally sourced interface. So there isn't any other interface that is currently available at the moment. So we can fix that, and we can create some more interfaces if we choose to. What I also want to double check on and make sure that I have connectivity from a layer 2 standpoint, and my layer 2 addresses are being translated into layer 3 addresses, is the usage of ARP, or address resolution protocol. So if I did an IPnet NS exec, let's exec into the orange namespace, and then did an ARP, nothing, because I'm not learning about anything at the moment. I haven't assigned any interfaces or IP addresses or anything of the likes. We will address that. But one key consideration, though, is if you look at the exec command, that's very, very similar to the Docker exec command, or the kubectl exec command, or kubectl exec, depending on how you pronounce kubectl. But the exec command is allowing you to execute commands in the process, or in the namespace itself, and effectively gather data or make connections or do a variety of other things. Now, if I were to run an IPnet not NSX, NS exec purple, because we'll look at the purple namespace, and run the route command, I have no routing. I'm going nowhere at the moment. So we're going to fix all of this. And the way we need to do this is we also have to create virtual interfaces for these network namespaces. We have to create virtual wires and attach one end to the network namespace while the other end goes to the bridge. We have to create a bridge, which we're going to do right now. And we also have to assign addresses as needed. So I'm going to create a bridge, and I'm going to call it super bridge. So IP link add super bridge 0. And we're going to basically type it as bridge, so we know that it's a type of bridge. We're specifying to the operating system that this is a logical bridge that's going to switch traffic for us between different endpoints. So it's MAC learning as well, MAC address learning. We also need to enable the bridge itself. So I have to go IP link set dev super bridge 0 up. And that just administratively brings the bridge online. So now it's online, and we can even check that by doing an IP link. So if you look at this IP link here, it is right here, super bridge 0. And then we know that it is up because I've set it to administratively go up. So the moment I start plugging in, like virtually plugging in processes with their wires into this bridge, technically what's supposed to happen is I should start learning MAC addresses as well. And that's cool, because in the physical world, this is exactly how it works. I have a physical switch, and I have physical endpoints where I plug in, cables into them. And the switch now learns about those MAC addresses of those endpoints and is able to exchange information, or basically repeat signals for us. So we brought the bridge online. We're now going to go ahead and we're going to create a pair of interfaces, one for the bridge side and one for the namespace side. So let's start with the purple namespace, and we'll go IP link add veth. Veth stands for virtual Ethernet purple, and this is going into the purple namespace. Type veth, right? So we're just specifying that it's not a bridge and it's an actual virtual Ethernet interface, and it's going to have a peer, and the name of that peer is going to be veth purple bridge. And you can think of this as when you see that, that's the port. That's the actual port of the bridge on the bridge itself. Meaning, like this right here, what I'm creating is the network namespace side, which is the actual wire end of that process, and it's connecting to the port veth purple bridge on super bridge 0. So it's like I have a switch port dedicated for that particular process. That's effectively all I've done. So the moment I do that, I now have a switch port and a virtual wire created, and we can easily do the same for the orange one. So we have two network namespaces that are now attached to the same bridge. So What we also need to do is we need to associate these virtual wires to their respective namespaces. So IP link set veth purple netns purple. And then all I need to do is up arrow, and I can just change this to orange, and I can just go a little bit further up here and change this to orange as well. And now we have these respective Ethernet interfaces in the respective namespaces. And now we're going to also associate those virtual Ethernet interfaces for the bridge onto the bridge, because even though we created veth purple BR and orange BR, we still need to associate them. So let's go ahead and do that. IP link set veth purple dash BR master super bridge 0. And then we'll just do the same for orange. And then that should be it. Let me just clear my screen here so we have some more real estate. So we do have a little bit more real estate. I love that. And now let's go ahead and add an IP address to the bridge itself. Actually, no, not the bridge. We're going to add an IP address to the virtual Ethernet interfaces on each network namespace, and then we'll come back and add it to the bridge afterwards. So the way to do this is IP netns, or you could do the short form of -n. Oh, kubectl -n dash and a namespace. That's the way that we can flag a namespace that we're trying to get to. So purple namespace here, and then I'm going to add the address 192.168.52.1/24 device veth purple. And part of the reason why I'm choosing this particular address is, remember, this is just an address in the subnet. This subnet can house up to 254 usable hosts, depending on which network engineer you ask. And .1 is just one of the addresses in that usable range. Oh, that's not good. Oh yeah, I forgot the IP ADDR command, and that's how I get my IP address on there. So now we also have to bring up the network namespace interface. So IP-N purple link set veth purple up, and that just brings the interface online. So if I actually were to do an IP-N purple IP link, oh, sorry, not IP link, exec link. Dang it, I'm not getting this right. IPnet ns exec purple link. There we go. So now you see this interface is online, right? And there's another way to see the addresses. So IP ADDR. And there we go. So now we have an address for the purple one, and I'll just do the up arrow here, and I can change this to orange. We don't have an address on orange yet because we never did it. So let's go ahead and create that address. I'm going to clear my screen, and we can up arrow and save us some time. And all I need to do is change a few things here, right? Because I'm going to do this for the orange namespace. I'm basically going to change this to orange. The next address that I'm going to add is 2. Okay, let me pause for a second. The other one had 52.1 as an address. This one is 52.2. Because of the /24, and if they are both going to be connected to the same bridge, super bridge 0, technically what will happen is that these two will be on the same broadcast domain, the same layer 2 segment, and the same layer 2 bridge or network. They can effectively communicate with each other. That's only after I effectively add all of this information. So let me just change this up to orange, and let me now check that there is an address. There is an address. And all we're going to do, oh, by the way, and to check that address, all I did was IP netns exec orange IP ADDR. And the only other thing I need to do now is bring the link online. So I will just change this to orange. So IP link that, sorry, IP dash N or IP netns orange link set veth orange up. All right, so now both of those interfaces are up. Okay, now what we're going to do is we're going to go ahead and assign an IP address to the bridge. So IP address, let me clear my screen. IP ADDR add 192.168.52.5/24 device super bridge 0. And if I do an IP link, the bridge is there. IP, let me clear this, IP ADR. And if we look at bridge 0, there we go. That's the address there. Perfect. Okay, so the very last thing we need to do, just so that we ensure some basic connectivity, is to bring these ports online on the bridge. So on the actual super bridge, we have to go and turn these interfaces online, because in a physical switch, there might be a reason, there might be circumstances where you disable ports by shutting them down administratively. So even if someone plugged a wire in, no one would be able to get connectivity. We're kind of doing the same thing here. We have to enable these interfaces on the switch itself or on the bridge to make sure that this works. So what we would do is IP link set dev veth purple -br. Remember, this is on the bridge side. We created this much earlier on, and we associated it to the network namespace virtual Ethernet interface process. We're going to bring this online, and then we're going to do the same with orange. And now we have those two online. Okay. So now what we can do is if I did a ping from my host system, right, to one of these network namespaces. So if I did 52.1, okay, that means I can ping the virtual Ethernet interface for purple, or the purple process. And if I did 2, that means I can get to both of them. So now, what if I actually decided to exec into one of these, and if I wanted to ping the bridge IP? So if I did an IPnet ns exec orange ping 192.168.52.1 is purple, right? I can't get to it for some reason. Let's try 52.5, but I can get to that. Okay, so I have partial connectivity, so something might be blocking. We'll slowly start to unlock this. Also, if I try to, oh, did I bring my interfaces online? Wait, I think I did not. Oh, wait, no, I did. Okay, so I brought them online. Okay, so now I need to just also go ahead and see if I can ping outbound. So from here, I should be able to ping the kubernetes.io website, right? Okay, so I can ping it. Now I know its IP address, so I don't need to dig for it. But what I want to try is if I did an IP netns exec orange ping that address 147.75.40.148, I can't reach it, right? Why can't I reach it? So let's do a dump of the route table. So interestingly enough, if you look at that route table, I only have a route to the local network that I know about. So theoretically speaking, I should be able to ping anything on that same segment. But what we need to do is we need to enable some additional features so that, one, anything that is originating from a network namespace has the ability to go outbound towards the outside world. And 2, we can also enable namespace to namespace communication as well. Because guess what? We have pods in our network that also need to communicate amongst each other. So let's go ahead and set up an IP tables NAT rule. So the IP tables NAT rule we want to apply, and I'll clear my screen again, IP tables -t nat dash a. And by the way, dash t stands for table. And then we're using the nat table, and then we're using dash a to accept. And then we're going to use post routing, specify a route specifically to 192.168.52.0/24, and we're going to masquerade. So the reason why we masquerade is because we're actually overloading the physical interface of the host itself, meaning we're going to use the physical interface of this host to get outbound to the outside world. Oh, I need to type in IP tables, not IP table. So to get to the front of that line, just type in Control A, and then we'll bring you to the front of your, or bring your cursor to the front of that line, so it makes it easy. Now, I've added the IP tables rule. Let's go ahead and see if we can ping. No, we still cannot ping. So what we can do is we can double check the route again, right? So the route is not there. We can add a static route. So one thing I will point out once we're done this exercise is some of the concerns around why you wouldn't do this in production manually. We'll talk about that shortly. But I'm going to go ahead and add a static route so we can get outbound. So we're using the orange namespace, IP route add default. By the way, if you're curious about what default means, I'll read this out to you so you learn a little bit more about how this routing works. So I'm execing into the orange namespace. I'm basically adding a static route, which basically says, if I'm trying to go to any destination that I don't know about, the only destination I know about is 192.168.52.0, well, use this address, 192.168.52.5, which is the super bridge 0, to get outbound. And as long as I have that, then I should be able to get to the outside world. So now that I have that route added, it should show up shortly. I'm not sure why it's taking long. IPnet NS exec orange route. Interesting. What happened here? IPnet NS exec orange IPRAD add default via. Then let's check my purple one, see what happened there. Okay, well, I have my default route. Well, I don't have a default route, but oh, I see. Wait, no, that should be fine. You know what? Let's try it with the purple one. I don't know what happened to the orange network namespace. So what we'll do is we'll up arrow here and we'll add the default route to the purple namespace. And I have a feeling that this should be fine. So if I do oh no, what happened there? Maybe I need to also enable systemctl forward wnet.ipv4.ip forward equals 1. There we go. Okay. So I was a little worried there for a second. Was I? I don't know. Maybe this was all part of the plan. But part of the reason why we have to enable IP forwarding too is because we're now telling the Linux operating system or the operating system itself that we want to enable traffic flow or traffic forwarding, meaning if anything is sending traffic, allow it. If it's a 0, which it was previously, traffic won't be allowed to move forward. But if you realize now, I have a default route in my purple namespace, and if I up arrow to my orange namespace, I also have a default route there too. The default route actually is 0.0.0.0//0, which basically signifies that it's an any route, so to any destination, and you will use the super bridge to get there. So, moment of truth. If I clear my screen now, and if I did an IP net NS, no, an IP net NS exec orange ping 147.75.40.148, which is the kubernetes.io website, it goes through. This is perfect. This is all great and well, but here's the reality. I want to point out something very, very important to us all, because the one key consideration here is that we're talking about two processes that I just created. And by the way, now that we have these two processes in place, technically speaking, if I did an exec orange ping and I did a 192.168.52 dot wait, one? Yeah. Wait. Let me just double check something. I just want to check the address because I wasn't sure. So this one is two. Okay. So if I did a ping to one, one is the purple namespace. So we know that the two pods or two network namespaces can communicate with each other. Okay. That's all good and well. Let's just quickly go back to this diagram for 1 second, right? Because here's where the magic comes in. We built this, we built this, we connected this to this, we connected this to this, we created this bridge. Well, before that, and then we expose this bridge through NAT. So now any traffic flowing from this network namespace or this one outbound, to the outside world, to the local host, local interface to the outside world, should be able to get through just fine because of that NAT, and also because we enabled IP forwarding. But the other interesting thing too is we're now able to communicate across to these two network namespaces can bidirectionally ping each other. Now, the reason why this is important is because when you think about something at production scale for a second, we have to assess that we're not going to simply do network namespaces for every single container that we need to create. We will use a system. The system is the CNI, the Container Networking Interface Spec, that basically defines a set of criteria, right? The pod CIDR that you'll use for your containers, which is the subnets that your containers are going to basically get IP addresses from, as well as an IP address management, kind of like DHCP, so that these addresses do get handed out to all of these pods, as well as an offboarding mechanism, meaning if those processes needed to be terminated for whatever reason, and if we needed to release that IP back into the pool later on after a given period of time, well, that needs to happen as well inside of this container networking interface spec. So that brings us to the end. That's actually how pod networking works. It's really about automating the onboarding and offboarding process using networking namespaces. And in fact, a pod is a network namespace. I'd like to thank you all for coming by today. My name is Marino Wijay. I hope to see you all in future episodes of 90 Days of DevOps. Thank you, Michael Cade, and the rest of the community. See ya.